Industrial Insulation Group. I have 17 years of experience in the building materials industry, with experience as a product testing lab manager for acoustics, thermal, and fire, and as well as experience as in product development engineer for commercial roofing. I'm a licensed professional engineer in the state of Colorado and a LEED accredited professional. If you have any questions that you'd like to submit, please put it in the chat box at the right-hand side of your screen, and we'll answer those if we have time at the end of the presentation, or if you give us, or we can respond to you through email. Just a warning, we're in Denver, Colorado. We're experiencing blizzard conditions. There have been power outages throughout Denver, so if by chance, the remote chance that there is any interruption in the webinar, we'll reschedule that for a later date. But again, we're not anticipating any problems. And again, thank you for attending, and look forward to spending some time with you this afternoon. Okay, what we're going to talk about today is thermal data. You have a lot of available resources out there, and some of them can be confusing or even misleading. We'll be covering the questions you need to be asking to ensure you're getting the right data so you can make well-informed decisions to estimate heat loss and safe-to-touch temperatures. We'll also be talking about thermal shift and what thermal shift is, how it impacts your system, and how to correct for it. We'll also talk a little bit about the material which is at risk for having this problem. Finally, we'll be talking about ASTM C16 corrosion. Now, not all passing results are the same. I will explain the differences in passing results and thresholds for ASTM C16, 17 for each of the standard industrial insulation materials. To start off with, insulation covers a very wide range of temperatures from as low as minus 450 degrees Fahrenheit all the way up to 3,000 degrees Fahrenheit. For industrial installations, and for the focus of this presentation, we'll be limiting that range to 61 degrees Fahrenheit to 1,500 degrees Fahrenheit. We do offer, Johns Manville does offer products that can be used in the lower end of the in the low temperature range. We also have products that can be used in the low end of the refractory range, but again, the focus is going to be primarily on the intermediate and high temperatures. Here's some examples of some insulation material types that we have. And note that the majority of the materials that are used in intermediate to high temperature ranges are silica based. Now there's foams, both plastic and glass, to provide better low temperature performance due to their inherent moisture resistant properties. The problem with higher temperatures and foam insulations is that the heat tends to deteriorate these materials. Cellular glass is also a good option for low temperature applications just because it has a pretty good resistance to moisture infiltration. We find intermediate and high temperature applications with these industrial processes, which primarily focus on refining, processing, power generation, manufacturing, and marine. Insulations that are used in these applications must be able to resist heat, physical stresses, vibration, and worker traffic. This is probably the most demanding insulation category that there is. Energy-intensive processes benefit from insulation for many reasons, and we'll talk about that on the next slide. As you can see, there's 9 good reasons to use insulation, but we'll go focus on really 3 aspects. To start off with personal protection from hot pipes and vessels, we want to make sure that we keep our surface temperature at 140 degrees Fahrenheit or lower because it reduce the risk of first-degree burns. Additionally, it provides a cooler work environment that reduces the risk of heat stroke. Now, if this piping happens to run indoors, the insulation can also help reduce the interior temperature of the building, which also lowers that air conditioning or heat load that you'll have. The second aspect here is improved process control. This is and heat conservation. The more that you can maintain your process within a given range, the easier it is to keep that process from fluctuating dramatically. This also means that you can count on using the same amount of energy going in, so you're not constantly trying to heat things up to compensate for heat that's lost through ineffective or compromised insulation. The other thing, and I don't think most people think about this, is corrosion protection. Corrosion under insulation is a concern with insulation, and some insulations have corrosion inhibitors to dramatically reduce corrosion rates. We'll talk about more on this on a subsequent slide. And of course, there are the other advantages that are listed here, but I think the focus needs to be on when you use insulation, you have less energy going in, which also means you have less emissions coming out as well. So the advantage to that, of course, is if you're limited to stack emissions, things like that, the more that you can reduce your emissions, the better. The first topic we're going to talk about is thermal data and the difference between insulating round versus flat surfaces. And we want to make sure that you're using the right information. The challenge is that there are several sources for thermal data. There's manufacturers' data sheets, trade organizations, the internet, and the American Society of Testing Materials, or ASTM. Now, the consequences of using the wrong data are increased heat loss, which is wasted resources and money. You have higher insulation surface temperatures, which means you have a higher potential for burns. And if it's inside, again, we have a higher likelihood of heat stroke and an increased air conditioning load. And the other thing that we don't normally think about with insulation is we want to make sure that we have a factor of safety with the products that we're considering using. That way it gives a little bit of flexibility and a bit of a cushion in our system. So in case something does become compromised, it's not going to be as bad when something has a safety factor built into it. Now, when we talk about thermal data, the first place that we start is looking at K values. And what a K value is the thermal conductivity of a material. And the units for that are on the left-hand axis, where we have where a K value, at least in U.S. units, is BTU inches per hour square foot per Fahrenheit degree. Or if in metric, it would be watts per meter squared Kelvin. Basically, what this means is this thermal conductivity is a measure of how much heat flows through a material in a given period of time. The lower the K value, the lower the amount of heat that travels through a material in a given period of time. So looking at this plot, what we have is 6 common insulation materials that are used for industrial applications. They range anywhere from the high winded expanded perlite all the way down to the lower lines, which represent the microporous blanket and silica aerogel products. Now, in all cases, note that as you go from a lower temperature of 100 degrees up to 800 degrees, the thermal conductivity goes up, which means the rate that heat flows through the material also goes up. This is largely a component of radiative heat transfer. Now, one thing to notice in particular, if you look at the mineral wool line, which is the third from the bottom on the left-hand axis, or left-hand side, indicates that it's one of the third best performing products, and also happens to be one of the least expensive. But as we go up the temperature range, note that the performance deteriorates at a much faster rate than the other materials that are shown here. So by the time we get to 800 degrees, we're the second worst product. Now, of course, there's other characteristics to take into account when you're specifying an insulation, but as you can see, the thermals don't always necessarily behave the same way between all the products. Now, how we test these materials is it's pretty simple in concept, a little bit more complicated in reality. Now, we're talking about the difference between a flat test versus a round pipe covering test. On the left-hand side, you'll see ASTM C518, which is the flat test. Now, because K values are a thermal property, we can measure that performance quite easily. We simply have a hot plate, which in this apparatus on the left would be either the top or the bottom. You'd have a cold plate, which would be on the opposite side of the hot plate, and you just simply measure how much energy that you have to put into the hot plate to keep everything at equilibrium. So as an example, for most building insulation, the hot plate would be at 100 degrees, the lower plate would be at 50 degrees for a mean temperature of 75, and you would only apply enough heat to maintain all those temperatures, and from that you can determine what that K value is. So I just used the 75 degree mean temperature reference, and of course with industrial insulation it starts at 100 and goes all the way to 12 to 1500 degrees. So the flat test is pretty straightforward. It's what they call one-dimensional heat flow, and those typically give the best results, or the lowest results, I should say. If you look at ASTM C335, it's a little bit different. Again, we're doing the same thing. We have a hot heat source, which is the pipe, and then of course the cold side was actually be the temperature of the room, which in most cases is somewhere between 70 and 80 degrees. Now the difference is, if I want to get it tested at mean temperature with C518, I only need 100 or 200 degree temperature difference. So if I'm testing to a 700 degree mean temperature, I might have a hot plate of 800 degrees and a cold plate of 600 degrees. Now with the pipe test, if I wanted the same 700 degree mean temperature, my pipe temperature now needs to be 1475 degrees, and then my room temperature at 75 degrees would give me a mean temperature of 700 degrees. So we have a much larger 1400 degree temperature difference. The other thing that we have here is there's radial heat transfer. Okay, so we're measuring heat transfer coming off something round. So imagine you have heat at the pipe, and then as it goes out in this pie wedge-shaped type of configuration, you have a lot more material to spread that energy over, so that's also going to have an impact on your results. Now, the challenge here is we're in a sense comparing flat versus round, but two very different test methods. Long story short is with pipe testing, our results are typically anywhere from 15 to 30% higher than they would be for a flat test, or as we state here, your flat tests are 15 to 30% lower than a pipe test. Again, there's a big discrepancy, but C335 does probably a better job of approximating real-world situations. The C518 is a better indicator of flat performance, or maybe the material property of the material itself. Now, again, the takeaway here is to make sure that you are using the right data for the right configuration. Now, the advantage that we provide to you is that our data sheets are always going to show flat surface values versus the pipe values. That way it'll make it easier for you to specify and determine what thickness you'll need for your particular application. So to start off with, we talk about material specs, and in this case we have calcium silicate. ASTM has a standard specification for all insulation material types. They have them for calcium silicate, perlite, mineral wool, microporous, and silica aerogel products. Now, looking at this set of data, we have ASTM C518, which is flat testing, and we develop a thermal curve. And how we do this, again, we started at a set point at 100 degrees. So we have a hot plate, a cold plate. We wait for everything to come at equilibrium. We take a measurement. We increase the mean temperature to 200 degrees. Wait for it to come to equilibrium. We take another measurement. We do that until we get to, in this example, up to 900 degrees. Kind of another giveaway that this is flat testing is we can go up to 900 degrees and still get a decent data point. Now, when we do the round testing, again, we have that mean temperature that's much harder to accommodate because we have to get our pipe temperature so hot. So if you look at the data here between 100 and 200 degrees, very similar, probably within the uncertainties of the test method, so there's some overlap there. But at 300 degrees, we see that things start to change a little bit. And again, we also notice that the pipe testing is translated up. So again, a higher value means we're going to have more heat loss than we're going to have with a lower value. Okay, and finally, this green line on top, this is what the ASTM standard specification requires for calcium silicate products. And again, note that it tends to parallel the pipe testing data. The advantage here is that if I have a product that complies with the ASTM standard specification, in this case C533, that means the materials that I show the data here for will meet that specification every time, and we're considerably lower here. In fact, if you look at the data point at 200 degrees, we're a little less than 4, and the ASTM requirement is it looks like to be 0.45, so it gives a considerable amount of leeway there. Now, if we look at all the products in this category, and just looking, for example, in the upper left-hand corner, you can see that the standard specification, and this is the slide that we looked at before, scaled a little bit differently. But you see that our ASTM line is the highest. Next, that we have our pipe data, and then below that would be our flat data. And looking over at scroll, you see the same thing. If you go down to the lower left-hand corner, kind of an exception here. We talk about mineral wool. ASTM C547 is for the pipe configuration, and that has thermal values that are in the standard. And then there also has ASTM C612, which is a board standard specification, and that has different requirements, which you can see is the higher line of those two greens. And if you look, but still, you know, the product is well below those lines. And then, of course, we have micropores in the lower right-hand corner. Now, one example that we have with Silica aerogel blankets, this is kind of unique in the ASTM standard specification in that you have both flat and round values that are in the same standard. The closest thing that we had on the prior example was mineral wool, where we had a different standard specification. You had one for boards, you had a different standard specification for pipe. Silica aerogel, they just incorporated those two thermal curves into one standard specification. So this is the line that you're going to see for flat data. There's another line, of course, for the pipe data, and of course the product has to be at or below that line as well when tested in a pipe configuration. Now here's the plot for flat data, and maybe kind of a giveaway, and this was actually from a Silica aerogel manufacturer's data sheet. So if you look at this plot, you can see that it goes up to 1100 degrees, which tells us it's flat testing. And notice that it lays right on top of the ASTM C1728 flat testing, the C518 testing. So looking at this, I think it's safe to say that that ASTM and the data sheet, they're in agreement as far as what the requirements are, and below the 1728 pipeline. The challenge, though, is that you can see that there's a difference between the two. C335 and C518, again, on a previous slide, we saw that it can be 15 to 30%. In this case, within the Silica aerogel standard, it's a 33% difference. Now, there has been a proposal to switch from just removing the pipe section altogether, which, of course, people have the right to do. But the concern is that number one, if you don't have that information there, how are you going to know which application this is for unless it's explicitly stated in the standard? But the other thing, if you look at the ASTM or the Silica aerogel line and the ASTM line, they overlap. Where on the previous slide, you can see that the products that were tested were below that ASTM line significantly. So there's enough room for production variation or installation defects, things like that, that you could get by with using something that had been compromised or something that maybe was a little bit off. But in this case, we see that because our data sheet and our ASTM requirements are kind of in line, we better hope that that product that we're using is going to perform the way it says, and maybe we need to add a factor of safety when we're specifying the Silica aerogel blanket to make sure that we're we do have any issues that we have enough thickness there to cover our thermal requirements. Now, the first question that comes to mind is, well, that's great, but where do we get this data? The good news is that NAMA, the North American Insulation Manufacturers Association, has 3E Plus software, which is free, and also it comes preloaded with ASTM standard specifications for all material types, or all insulation material types. And so, as we've been talking about, even preloaded into this software, we have aerogel flat versus aerogel pipe, and it has the ASTM requirements already built into that. And if you look at even the duct wrap product that's shown above, it shows the different densities, and then the ASTM, in this case 1290-11, it shows all the different thermal values for those products. So again, this doesn't come from manufacturer's data, but it comes from ASTM, and something that's already preloaded. So you don't have to go out and look for this data, it's already there. Now, here's the one thing that we haven't really talked about is a real-world example of why do we even care that there's a difference between flat versus round data. Looking at this example, we used an 8-inch pipe, 2,600 feet in length, under the conditions shown above here. And if you look down at the product that was used, if you would have selected the C518 data in the 3E Plus software, versus C335, you would have had a 12-degree temperature difference, which would have put you from a below 140-degree safe to touch temperature to 150, which means you would burn within a second after touching that hot surface. There's also a 57 BTU per hour per foot difference, which doesn't sound like a lot, but when you're talking about long lengths of pipe and over long periods of time, going through our example, you see that that's almost $7,000 a year. which is almost $140,000 over 20 years. So this is real money, and this is even a temperature that's not, you know, if you have higher temperatures, longer lengths, these types of savings add up very quickly. So there's a real-world consequence to using the wrong data. And again, it's a lot easier to add an increment as you're putting things together rather than having to go back and try and fix a hot surface or a system that's using more energy than it's supposed to. So we talked about round versus flat testing and the potential implications of using the wrong data. Now that we know what information we can rely on, we can move on to thermal shift. And again, we want to make sure that we're looking at this, making sure we're using the right things so we improve our process efficiency, we're saving the money that we're supposed to, maintaining our safe-to-touch temperature, and making sure that we have a good system that we can rely on. We begin our next topic. This is thermal shift. It's a permanent change in material conductivity of an insulation material. And there is a material that is at risk. Now, we started this discussion with a definition. It's the permanent change in an insulation material's thermal conductivity due to several hours of exposure to high temperatures. Now, the implication here, of course, is that the thermal conductivity is going to increase, which is going to allow a greater rate of heat transfer, which means higher rates of heat loss or higher safe-to-touch temperatures. So, you know, why is thermal shift bad? And when we increase thermal conductivity, we increase heat flow, we decrease thermal performance, we have higher heat loss, surface temperatures, we have increased, and because we have those increased heat flows and higher surface temperatures, we have increased burn potential and higher operating costs. So the material that's affected by this is the silica aerogel blanket. The traditional insulations that we talked about earlier, the calcium, silicate, mineral wool, perlite, and microporous insulations aren't affected by this. To give you an example, this is what we tested, and this was done using plot testing, but again, note on each one of these plots we have the ASTM line, which is the purple line translated up from all the other lines. Now the two lines below it represent, we did testing, which we described earlier, where we tested each individual set point, we let everything cool, then we tested it again. And what we saw is that there are some very slight changes, as you can see with the Thermal 12 Gold calcium silicate product, and maybe a little bit with the Insulate HT product, but generally speaking, those differences are very small, and one could argue that those are within the uncertainty of the test method. But I think it's fair to say those results are equivalent. There's no real change in the thermal performance of these products, and they perform significantly better than what their ASTM standard specification requires. Now, we did the same test with the silica aerogel blanket, and what we found is this. We start off with the ASTM C1728 maximum, which we saw in an earlier slide, and just below that, the blue line, we see the first cycle of flat testing that we had done with the silica aerogel blanket. For the most part, you can see that most of that product performs below the line, which is good. Some of the higher temperatures it's above, you know, does it pass, does it fail? I guess it depends on which temperature that you're using, but you know, maybe you could argue that it's close enough if that works for you. In my mind, it either passes or it doesn't. But when you test this product the second time, you see that the thermal performance translates up, and then at no point does that product meet that specification, and it's considerably lower than that. So that's a problem. That's, again, we're not talking just a few BTUs. This is a lot of energy and a lot of temperature that we're dealing with here. Now, this isn't something that is just specific to JM. We sent this to an outside lab to test this, to verify this, and this does occur. And we'll see more about this on a subsequent slide. So if we're looking at this, comparing this to the C335 round or pipe testing, again, we see the same thing. There's a translation as it translates up when we test it the second time. If you look at the two lower lines that are overlapping each other, that was our Insulate blanket insulation that we also tested in the same configuration. And note that you can't see any appreciable difference between the two. So, and again, if you look at the way the product performs at the higher temperatures, it does a really good job. So the big question is, what exactly does happen to the Silica aerogel product? Well, what happens is part of the requirements for the product is that a hydrophobe is added to help resist, to give some water repellency. But this hydrophobe oxidizes at 300 to 600 degrees. Now, as this hydrophobe oxidizes, the aerogel structure is compromised, which results in a fracturing of the aerogel matrix, which means it just breaks everything up. And now when this happens, the thermal performance is permanently compromised and heat-affected areas are no longer hydrophobic. Because we've already fractured this, we can't put everything back together again. And because this happens, our thermal performance will degrade to roughly the performance of the needle glass mat that is used as a substrate for this blanket product. But I think one picture is worth 1,000 words, or maybe 2 pictures. If you look at the image on the left, this is what the aerogel, or what aerogel typically looks like before it's exposed. Now, if you look at it afterwards, and this is the same material, not the exact same material, but we heated some material out of the same batch, and we used some that we just left at room temperature. As you can see, under the same magnification, it's a much smaller particle after it's been exposed than it is when it's larger. Now, what aerogel does is provides all these small air pockets, but if all these air pockets are fractured and turned into much smaller pieces, there's nothing there to help reduce that heat transfer, that heat flow through the material. Now, the other thing, because we've oxidized that hydrophobe that's on there, that now our product is no longer water repellent when it's been exposed to temperatures of 300 degrees or above. Now, because it does cause a permanent physical change, and we do know that this happens, there's a way to work around that. Now, kind of combining our first point that we talked about round versus flat data, we're going to combine that with thermal shifting to show how we can get around this. Now, if you look at our first example, it's an 800-degree pipe, and we have using flat design ASTM data versus our thermal shifted data, and you can see that if we use our design data, we're at a 45 millimeter thickness with a surface temperature of 138 degrees. But if we use the thermal shift data for the same thickness, now our surface temperature is 150 degrees. Now we need a 55 millimeter thickness to get our surface temperature back down to 140 degrees. So of course, we know that our pipe data is not going to perform as well as our flat data. So our initial thickness, we start with a 55 millimeter thickness for 140 degrees. But again, if we use our thermal shifted data, surface temperature is now 166 degrees. So again, we have to add additional thickness, or 10 millimeters, to make a 65 millimeter thickness to get our surface temperature down to 140 degrees. So long story short, those materials can be used, but there are some things that you need to do to make sure that if you are going to use that material, you're going to have to add at least one layer to make sure that you're bringing your temperatures and your heat losses down to what they were prior to that compromised value. Moving on to our final topic, we're going to talk about ASTM C1617 and that not all passing results are the same. Now, in the course of construction and maintenance, it's necessary for insulated equipment to be idle for long periods of time. And during this time, moisture can and most likely does infiltrate the system. It's usually exposed through either sudden storms, improper storage, improper installation, damage to the jacketing, or damage to the lagging. All the above can allow moisture to penetrate into the system. Now, all these scenarios create a potential situation for corrosion under the insulation, and the results can be catastrophic, and we see that in these pictures here, where things corrode to the extent where things rupture and actually can create some very significant damage, and not to mention downtime. Now, what we need for corrosion to happen is an operating temperature of 100 to 350 degrees. Now, corrosion can also occur outside of that range, and I think we know that, but this is the sweet spot for corrosion. We need oxygen, we need liquid water to be present. Now, water vapor or high humidity conditions doesn't contribute to corrosion. You need to have a liquid to help conduct or facilitate corrosion. You need corrosive chemical compounds, which are typically chlorides found in seawater and drinking water, and then acidic pH, which means it has to have a pH value of less than 7. And again, every insulation type in just about in that temperature range is going to fall in that, whether it's a polyiso foam or whether it's a calcium silicate pipe insulation. Now, there's a new method that was developed by many manufacturers, and corrosion testing is always a problem because you always want something that's quick enough to be able to model real life, but also has to be realistic and applicable. And in this case, this test method is applicable to carbon steel. And the advantage that it has is it's more of a quantitative than qualitative, or that you have with some of the other methods. And it's also developed mostly for carbon steel, which it typically isn't. There aren't as many test methods out there for that. Now, what's involved with this test is the insulation material is ground up with distilled water. You take a metal coupon and you weigh it, and then you glue a tube to it, which you see in the image on the right-hand side, and you drip this insulation solution on top of the plate that's heated to a temperature of 230 degrees plus or minus 10 degrees. The point is that as this water boils off the surface with this leachate, that creates a very corrosive environment. So that's what we're trying to simulate, but it's not to the point where you're dropping water on something that's really hot, or trying to boil the water off because it wasn't hot enough. But it's just the right mixture of boiling to corrode that. Now, once the test is run, and it's run for 96 hours, those coupons are cleaned and then they're weighed, and then that change in weight is used to give you a mass loss corrosion rate in mils per year, or an MCLR. Now, whenever we run this test, just to make sure that you're not running it in a vacuum, you always want to make sure that you have some control that you're using as a reference point. And so, and there's 3 that are typically used, and 4 that are available, but 3 that are typically used. One is a DI water, or deionized or distilled water, which has less than 0.1 part per million of chloride solution. There's a 1 part per million chloride solution and a 5 part per million chloride solution. So the higher the concentration of the chloride solution, the higher the corrosion rate. So what happens is, when we get done, is that we have a kind of a ranking here, and so going from left to right, mineral wool, and even jumping in the middle where the pre-2002 calisol, you have pretty high corrosion rates. Silica aerogel is a little bit better. You look at Insulate and DI water, they're about the same. And then you have the Thermal 12 Gold and the Scroll products, which are below DI water. So what this means in terms of corrosion, if you look at the boxes on the left-hand side, is your deionized water has a mass loss corrosion rate of about 6.4 mils per year. The 1 part per million chloride solution is more like 41 mils per year. Now, so when we look at all these materials pass their respective ASTM rates, but as you can see on here, there's very different corrosion rates. So now, one of the takeaways here that you know, the pass rates are established determining by whether you're using deionized water or the 1 part per million chloride solution. So in this case, using the DI water reference point, the Thermal 12 Gold and the Scroll perform much better than that standard. And the Insulate HT is consistently below it, but at times flirts with that threshold. So, but the Thermal 12 and the Scroll consistently are better than that. Now, if you look at the mineral wool products, the Silica Aerogel, they're always consistently below the 1 part per million chloride. So even though they're below a given threshold, you can't say that their performance is equivalent. And maybe one example of this is that we've talked a couple times about standard specifications for insulations. So if you look at the blue boxes at the top of the table, we start with the ASTM C533, which is calcium silicate, and their requirement is that the corrosion has to be less than the DI water reference, and in this case it does. And as we saw in the previous slide, it's significantly lower than what that threshold is. Now, if you look at ASTM C1728, which is for flexible aerogel insulation, or ASTM C665, they use a less than 5 part per million chloride solution. And again, that's the most corrosive reference that there is. You could go as high as 10, but those are extreme cases. Now again, looking at pass-fail, they pass their respective requirements in that they're less than 5 parts per million. But if you're comparing it to the DI water limit, they would fail because they're above the DI water, but they're below the 5 part per million threshold. So again, when you say that it passes C1617, you also have to ask, well, at what limit? Again, this is a test, and tests are always open to interpretation. So a test just gives us a result, but the standard specification gives us a criteria as to whether that passes or not. So in this case, the calcium silicate is going to perform much better in this situation than the flexible aerogel blanket with a mineral fiber blanket. So just to give you an idea, here's some actual metal coupons. And if you look on the left two for either the Sprule or the Thermo 12 Gold, which have the XOX inhibitor, you can see that there's very little degradation to the face. No pitting, no gouging. It looks almost like new metal. If you look at the calcium silicate pre-2002, you can see there's a lot more activity or degradation that was done when they tried to clean that off. So there's a lot more corrosion going on there than there were with the other products with the corrosion inhibitor. So to summarize, when we're looking at ASTM specifications that have the same passing requirements, you need to understand the different corrosion potential for each material. So ideally, if you want to use a corrosion inhibitor, hydrophobic installations aren't a bad idea. They help repel water, but again, that's only part of it. What are you going to do when water gets into your system and comes into and stays in that place between your pipe and your insulation? You want something there that's going to be able to take care of that. And again, a passing result, you always want to look into that and understand what is passing. Is it an A+ if you get less than DI water, but maybe it's a D if you pass 5 parts per million. It all depends on your threshold, and then clearly if you want to minimize corrosion, you want to use the lowest threshold as possible. Now, to summarize what we've talked about, now with thermal data, we know that there's pipe and flat applications, and we always want to ask the right questions and use the right data because it does make a difference, as we've seen. And depending on the temperature and the application, it could be substantial. We talked about thermal shift, which is a permanent change in an insulation's thermal performance, and we know that it happens in applications above 300 degrees Fahrenheit. And knowing that this occurs, a designer can compensate for the degraded material by adding additional layer or layers of insulation. So again, you want to use the 3E+ software and try and figure out, how many layers. In our example that we saw at 600 degrees or 800 degrees, we saw that it was one additional layer. Finally, for ASTM C1617, not all specifications have the same passing requirement. Again, it depends on the product type, and there are different passing limits for C1617, and the calcium silicate is the most stringent. Want to make sure that you keep that in mind. So this concludes our presentation. I want to thank you for attending. We have a few minutes left, so I can answer any questions that you might have. If we can't answer them here, please feel free to give me a call, or we can email you a response. One other thing I would ask you to do is we have a survey that's going to show up after the presentation. We're always trying to provide content that's useful to you and ways to improve what we currently have. So if you can fill that out for us and let us know how we can improve, it'd be very much appreciated. Well, thank you so much. Have a great day, and thank you for tuning in.
Explain once again why the thermal shift only happened to the aerogel material.
Okay, the aerogel material has a hydrophobe that they add to it, and what happens is it oxidizes when it starts to oxidize at 300 degrees, and it's completely gone at 600 degrees. Now, as it oxidizes, it also seems to be part of the structure, which, as it oxidizes, it causes that aerogel to fracture. Now, when it fractures, it can't trap as much air or impede thermal, heat energy as it's traveling through the insulation material. So when that happens, you basically have this large piece of material that once it fractures, now he can freely go around it, and that's the degradation that you see in that. And again, as we saw on that slide, that's the rupturing of the aerogel as it's breaking. That's what compromises the performance.
Can you explain one more time why thermal shift does not continue to worsen over time?
Okay. Every material has a thermal performance that's kind of inherent to it. So even though the aerogel blanket product is actually it's an e-glass needled glass mat. It's high density of about 12 pounds per cubic feet. That's per cubic foot. That is the aerogel matrix is kind of embedded or infused into this blanket. So even though that aerogel is compromised, you still have the thermal performance of that blanket itself. Any insulation material, it never goes to zero. It always has some value to it. You know, whether it's a binder burning off of mineral wool or you know, aerogel fracturing, even the substrate that's embedded in still has some thermal performance to it, and so it's always going to have at least that material's thermal performance.
And let's have three more. Can you explain once more in a sentence or two why there's a difference in thermal conductivity in a flat surface compared to a round surface?
Okay, biggest differences are number one, you have a radial heat flow, so you're going from a center, kind of moving outwards in a circle, so that's part of it. Number two, very large temperature differences with when you do round testing versus flat testing, so that's part of it. And then the third part of that is there's just much better control with flat testing than there is with round testing, so there's a higher degree of uncertainty with pipe testing than there is for flat testing.
There's a question, I think, Doug, that's probably better answered in an email about the thermal conductivity formula for flat versus round. So that one we will answer in an email because it involves formula question. So, and the last one I have here is, so in the corrosion test you talked about, even though all the insulation you showed had different results, they all did pass the test, correct?
That's right. Every standard specification for materials. In the example we used, we had silica aerogel, mineral wool, and calcium silicate. And in each one of those three standards, they have a requirement that you have to pass ASTM C1617. The difference is that calcium silicate had a passing requirement of being less than DI water. Now the calcium and the aerogel and the mineral wool had to be better than 5 part per million reference. So they all passed their respective standard specifications, but the numbers are actually different. They just have different pass rates in each of those standards.